Hi students. In this lecture, I am going to discuss problems from Irodov. Let us see first one. Two horizontal disks rotate freely about a vertical axis, passing through their centers. The moments of inertia of the disk relative to this axis are equal to I1 and I2, and the angular velocities omega 1 and omega 2. When the upper disk fell on the lower one, both disks began rotating after some time as a single whole due to friction. Find the steady state angular rotation velocity of the disk. Second one, the work performed by the friction forces in this process. Right, see the question. Right, now see how to start. Suppose Suppose this is a disk, axis is now vertical. That means imagine this board plane is horizontal and we are seeing from the top. So this is now axis, which is vertical. Let us say rotating now like this. Now on this, we are placing one more so that both having same axis of rotation. And that second one may have omega in the same sense or maybe opposite. So now here we are going to use conservation of angular momentum because about this axis net torque equal to 0. Then say what we are writing here. It is I1 omega 1 bar plus I2 omega 2 bar. See finally what happens. So when you are placing the other one on this one, between these two disks because of friction, after some time, they come to have same angular velocity because of friction. That means finally it is I1 plus I2 into omega bar. So this is according to conservation of angular moment. Now in this we have to focus the sense of rotation. Suppose if omega 1 bar and omega 2 bar are both in the same sense, that means both are clockwise or both are anti-clockwise, then this becomes I1 omega 1 plus I2 omega 2. That is equal to I1 plus I2 into omega. That means omega value I1 omega 1 plus I2 omega 2 by I1 plus I2. This is if both are in same sense. Suppose one is clockwise, other one anti-clockwise. Then one is positive, other will be negative. Then I1 omega 1 minus I2 omega 2. Or you can take a difference, okay? So whichever is more, that is equal to I1 plus I2 into omega. So we have to focus the sense of rotation. So here I have taken both are in same sense, both clockwise or both anti-clockwise. Here, one is clockwise and one is anti-clockwise. Okay. Now see in the second part, the work performed by the friction forces in this process. So in this process, because of friction, we can see here, since they have different omega values, they are slipping on each other. and because of slipping, energy will be lost. That means by friction, work done will be negative. See how to write? By frictional force, work done, that is equal to final kinetic energy minus initial kinetic energy. Okay. Final kinetic energy means half I1 plus I2 into omega square, because both have same omega value. That's why half I1 plus I2 into omega square minus initial value half I1 omega 1 square plus half I2 omega 2 square. Okay. Now here this value depends on, again, what is omega. What is omega? That depends on whether omega 1, omega 2 both are in same sense or opposite. Okay. If you're taking same sense, I1 omega 1 plus I2 omega 2 upon I1 plus I2. Opposite, I1 omega 1 minus I2 omega 2 by I1 plus I2. That is what we have to substitute here. So this value depends on what we are choosing here. Okay. So here I am generalizing. So this will come negative because energy is lost. This will be minus half I1 I2 upon I1 plus I2 into omega 1 difference omega 2 whole square. Wait, here in the place of difference, let me correct it. So there we have to consider, plus or minus. Okay. If you observe carefully, when omega 1 and omega 2 both are in same sense, energy loss will be less. Okay. So in that case, we have to consider here omega 1 minus omega 2 because loss will be less. Okay. If you are taking omega 1 and omega 2 opposite, energy loss will be more than we are taking omega 1 plus omega 2. Okay. So I will write here. So plus if if so we are taking plus, that means loss is more, we are taking plus if one is clockwise and other one is anti-clockwise, means opposite. Okay. Because in that case loss is more. More means, so anyhow this is a constant. Okay. So this should be more, that's why omega 1 plus omega 2, right? And minus if both are clockwise or both are anti-clockwise. Okay. Either both clockwise, both anti-clockwise, means both are the same sense. Then loss will be less. That's why minus. Okay. If they ask what is energy lost, you can see here energy lost is equal to negative of work done by frictional force. Okay. Because energy lost means final value minus initial value. That means we should take this final value minus, sorry, this initial value minus final value. So we get positive. And that's why I'm writing here energy lost equal to negative of work done by frictional force. Okay. So I hope you got a clarity. Let us see next one. A conical pendulum, a thin uniform rod of length L and mass m, okay, rotates uniformly about a vertical axis with angular velocity omega. The upper end of the rod is hinged. Find the angle theta between the rod and the vertical. Okay. So here conical pendulum means earlier we have learned a massless string and one particle. Okay. Now it is a thin uniform rod given length L, mass m, fixed at the upper end. We have to find angle between the rod and the vertical. Okay. So rotates uniformly. Condition is rotates uniformly about a vertical axis. Right. Let us see how to find it. Right. First make a diagram for this one. This is now support. Let us take this is now vertical. That is now vertical. Now rod is making an angle theta with vertical. Now rod is making an angle theta. This is now rod. This rod is making an angle theta with the vertical. This rod is now rotating about this vertical axis with a constant angular velocity. Okay. So we have to find now this angle how much. So theta how much. Then see what we are doing here. So we are solving this question from a rotating frame. So since rod is having omega, we are taking a rotating frame which is having same angular velocity. I am repeating. We are solving the question from a rotating frame which has same angular velocity. You just imagine there is a person here. Okay. Now he is rotating with the same angular velocity. Then for him, this rod always appears to be at rest. Okay. That means in that rotating frame, rod will be in equilibrium. That means net force equal to 0, net torque equal to 0. Right. Now see what we are doing here. So one thing we can take torque due to gravitational force. So gravitational force passing through center of the rod. You can see here torque due to gravitational force should be balanced by it. Since we are taking rotating frame, we should take now pseudo force on each and every element on this rod. And if you observe, different points are following now different circles. Means when we see from ground frame, when this rod is rotating, different points are following now different circles. For example, I am taking here one element, let us say its length equal to dx. Length dx, we are taking now at some distance x. Okay, or let me make diagram separately. So we are taking here one element of length dx at a distance x from the axis of rotation. So taking from here at some distance x, dx length. This is now theta. If you see carefully in ground frame, this element follows now a circle of radius that is equal to x sine theta. Okay, it follows now circle of radius x sine theta. But when you are taking now rotating frame, then we have to take here pseudo force. That is now m r omega square. M is m by L into dx. Mass of that element m r equal to x sine theta, m r omega square. This is now pseudo force. We want to calculate now torque due to pseudo force. We can see here about this point, torque due to pseudo force. It is anti-clockwise. It is anti-clockwise. And torque due to gravitational force, it is a clockwise. And these two should balance. These two should balance. Okay. See what we can do here. Torque due to gravitational force, that is equal to mg into perpendicular distance. This is L by 2 because center of mass L by 2 sine theta. So mg into L by 2 sine theta. That is a torque due to gravitational force. So we want to calculate now torque due to centrifugal force. Okay. So like this we have taken. See torque how much? It is m by L into dx. That is mass. R is x sine theta. M r omega square. This is centrifugal force into perpendicular distance. You can see here that distance will be now from here to up to here. Okay. So this length will be equal to x cos theta. Okay. It is now x cos theta. That is now torque due to this pseudo force. Like this, we have to consider torque due to pseudo force on each and every element. That means we have to integrate from 0 to up to L. That is a torque due to pseudo force. Now take constants outside. M by L, sine theta, cos theta, and omega square. So m omega square upon L, taking outside. Sine theta, cos theta, taking that also outside. Sine theta, cos theta. Remaining is now x and x square. X square dx. It is x cube by 3. Now take limits 0 to L. X cube by 3. It becomes now L cube by 3. Okay. So 1 L cancels. Remaining L square. This is now torque due to pseudo force. Okay. Now see equating these two. So torque due to pseudo force m omega square sine theta cos theta. What else left here? L square by 3. Cross check once. M omega square sine theta cos theta L square by 3. That is equal to. This is a balancing mg L by 2. mg L by 2. mg L by 2 sine theta. So sine gets cancelled and 1 L gets cancelled. M gets cancelled. So here cos theta equal to, it is 3g upon 2L omega square. That is our final answer. Okay. So here we have solved this question from a rotating frame. Okay. But we can solve same question from ground frame also. So if you want to solve, I'm giving hint here, you can try it. In ground frame, about this point, about this point, net torque is not zero. Because about this point, because of gravity, torque is there. This is now net torque. I am repeating, about this point, because of gravity, torque is present. This is net torque. This net torque equal to dl bar by dt. That means first we have to focus how to get angular momentum for this rotating rod. Okay. Students, if you remember, while discussing question number 46, which is a previous IT problem, having a massless string massless, having a point mass like this. There we have done calculation for angular momentum. There we got two components. One is along axis of rotation, which is a constant. The other one, normal to axis of rotation, which is a changing only direction. That means about this point, angular momentum is changing. Okay. So now we have to find that angular momentum for this rod. Then take dl bar by dt. That gives us net torque. And that net torque equal to torque due to gravitational force. Then we are going to get again same answer. Okay. So you can try that.